So this is part 2. The last round, for those of you that are going to hang on that long to see the final event, is next Tuesday, same time and place. So as is our tradition, we're going to have students introduce each other. So Mike is talking last, and we'll introduce our first speaker. So take it away, Mike.
Welcome, everybody. Our first presentation today is Sequence, Stratigraphic Correlations and Depositional Environments of the Late Ordovician Sequence in the Wells Outlier. Her favorite color is gold. Her favorite mineral is gold. From Akron, Ohio, Annie Bender-Preston.
As Mike said, I did my senior thesis project on upper Ordovician carbonates from Wells, New York. That research began this past summer, and I did my work with Bruce, Tamor, and Becca. Data for this study came from a limestone quarry called the Greymont Quarry, which is located in the south central Adirondacks. This quarry is an active limestone quarry which produces crushed rock for construction purposes. While we were at the quarry, we collected samples from 3 core boxes that were drilled in 2006, B1 2006, B2 2006, and B3 2006. They also had access to the quarry itself and the exposed stratigraphy in the quarry walls, which we call our measured interval. In addition to the samples from the Greymont Quarry, we looked at Crown Point, which is in the northeastern Adirondacks, and samples along New York Route 8, which is right off the blue line of Adirondacks. The Wells Quarry is within the Wells Outlier, which is a downdropped graben consisting of upper Cambrian to upper Ordovician strata. This is considered an outlier because it sits within the Precambrian material that makes up the majority of the Adirondacks, while there is preserved younger Cambrian and Ordovician stratigraphy. An interesting thing is that this graphic was produced in 1916, which was the first set of studies done in this area, which has been going on for an entire century now, so that's pretty exciting. The green is the Precambrian basement material. The pink and orange through here is the Cambrian to Ordovician, and this blue smiley face represents the Wells Quarry, Greymont Quarry. So my methods. While we were in the field, we spent 3 days at the quarry site collecting stratigraphic descriptions and looking at our core boxes and the quarry walls. We came back to Colgate and began our sample prep. This mostly included cutting slabs from the bigger samples out of the quarry walls and preparing thin sections from smaller cuts that we had from the core boxes. To look at what these rocks actually look like, this is from the quarry wall. This is one of our samples that sat just above an ash layer. You can see that these carbonates are rich in fossils, and they ended up looking like quite different through the stratigraphy, and you'll see that later on. In addition to preparing thin sections, we did some SEM work to identify euhedral zircon grains for age dating. And my final step, which is what I focused on in this project, was looking at the sequence stratigraphy and linking that to regional geology in other sections of New York. So the big question here, what exactly is sequence stratigraphy? Using the sequence stratigraphic approach, strata are divided into depositional sequences bound by unconformities, which are interpreted as resulting from larger allocyclic sea level change patterns. The basic way this works is you have a high stand, where normal depositional settings are occurring, shallow water carbonates in this case, followed by a period of sea level fall, which exposes the already deposited rocks and makes them susceptible to erosion. After that erosion surface has been formed, there is a flooding event as the sea level rise starts again. And how this differs from other correlative tools, prior to sequence stratigraphy, which is based more on age relationships and finding the actual age of the data or the strata to correlate over large areas. Prior to that, it was mostly through lithologic comparisons, just looking at descriptions of stratigraphy and matching that to descriptions in other areas. So the geologic setting of the time, these units are from right around here in Adirondacks. It was a large basin setting just to the west of the eastern margin of Laurentia. We were looking at the Black River and Trenton groups which were deposited between 457 and 450 million years, just about a 7 million year period, in a warm, shallow carbonate system. So this occurred right at the onset of the tectonic orogeny, which was happening with the accretion of island arcs onto the eastern margin. That caused significant tectonic loading of this eastern margin, which then caused a series of faults to produce basin subsidence, and we will see that as I continue through this presentation. That caused a shift from shallow water carbonates into a system of deeper water mudstones and shales. Becca will talk a bunch more on this in the upcoming talk. Before we go into my key findings, I want to introduce the sequence stratigraphic framework that I use for my study. So right here, there's a series moving up, moving from, here I can explain this a little better, coming up here. This represents a period of water getting shallower, and then the blue line, shifting to this triangle that's getting smaller, then represents a flooding surface moving into deeper water. So where those triangles meet, that represents a depositional unconformity with an erosion surface. To put my units into this structure, the lower Black River group, which is the base of my stratigraphy, is within the M4 sequence. The upper Black River is within M5A. Lower Trenton group is also in M5A, and then Upper Trenton, which is above what we saw in the Wells Outlier, is in the M5B. An interesting thing to note is with the onset of the tectonic orogeny, there was more activity, so these sequences became much shorter and closer together as that became a very active space. So the first key finding was the location of the Knox unconformity. This represents a period of erosion, beginning with the deposition of the Black River group above it. The Knox unconformity marks the separation of the M3 and M4 sequences. With this evidence, we were finally able to assign our group and formation names to our stratigraphy and start to piece together the exact age groups and stratigraphy that we had at Wells. So taking a closer look at this core box, which is from the third drill core at the Wells quarry, you can see the Knox unconformity right here represented as a sharp erosional surface. In a usual depositional setting, you would expect to see this shallow water sandstone having more of a gradational movement into this deeper water mudstone, but instead we see this sandstone of the Galway Formation, which is part of the Beekman Town group, a sharp contact, and then the calcareous mudstones of the Lauville Formation, which is in the lower Black River. The other key piece of evidence was the MH marker bed. In the field, we tentatively identified this as an ash layer, and then back at Colgate, we were able to find those euhedral zircons, send out samples, and date it. Taymor and Bruce did that work and came back with an age of 443 million years, plus or minus 14.6 million years, which puts this in the age range of the Bronson Hill Arc, which was active off the eastern margin from 454 to 442 MA. Taymor did discuss a bunch of that on Tuesday, so I won't go into it. But this ash bed is identified as the MH bentonite, which is within the House Creek member of the Lauville Formation at the base of the Black River group. To put this in perspective with our sequence stratigraphy, this is in the upper portion of the M4 sequence. So these are three of our stratigraphic columns from Wells, and you can see the link between this ash bed throughout the whole study area, which pretty much fits the dip of the area, which is about like that. So even on the small scale, we can use it as a linking tool. Okay, so to take this up to regional correlations, this sequence that we found at Wells can be found in other upper Ordovician units in other regions of New York. Before we go into that, this is from the third core at the quarry. And even in this stage of it, you can see the movement from sandstone to dolomite, and then the Knox unconformity, and then into deeper water settings with mudstones and shales. So in the towns of Brownville, Glen Park, Martinsburg, and Lauville, which are all toward the Great Lakes, we see similar stratigraphy, and this stratigraphy also shows that same pattern. So this is the Black River group moving up into the Trenton, which are the same age units that we saw. And you can see the shift from these coarser grained sandstones up to a setting with more shales and mudstone dominated lithologies. So during deposition, another interesting thing about sequence stratigraphy is that you see these broader patterns recorded in the stratigraphy, but within that, between locations, there are going to be slight differences in what the stratigraphy actually looks like. This is due to local influences, such as the input of fluvial material, local storm events, differing erosion during the low stand periods, and differing degrees of sedimentary deformation, which can result in, like, even if you're comparing a couple of these, they look slightly different. And that's one of the big strengths of sequence stratigraphy, is you can find those underlying patterns through the slight variations. So to bring this all together, this study aimed to set a better understanding of the upper Ordovician strata at Wells and incorporate that into the broader understanding of our regional stratigraphy. This sequence stratigraphic approach provided the MH bed and the Knox unconformity as key marker units to divide our units into formations and groups. This study also helped connect volcanism and eustatic sea level change, which are over the larger geographic area, to correlate units in geographically isolated regions, such as the Wells Outlier. Because it's so isolated in the Adirondacks, it's very interesting to finally put units in this big white spot. And that's all I have. Thank you very much. I want to thank the Geology Department and especially Bruce, Taylor, and Becca for being great research partners. Does anyone have any questions? Yeah.
How did you determine if the sequence was shallowing upwards versus deepening upward?
Let me go back to our sequences. So we are only looking at one sequence specifically, mostly the M4 sequence. And within this sequence, we saw a big shift from sandstones at the base of our units, moving upward into mudstones and shales. So we interpreted this as a deepening upward trend. And then from here, since we only had one time slice in our outcrops at the quarry, I then compared with literature and looked at a further extent of the stratigraphy to see that it was part of this larger deepening shift toward a basin environment. Yeah.
You mentioned that there was a strong transition zone between a sandstone and then a mudstone.
Yes.
Did your investigation in the literature kind of bring any further information to why that might have happened?
Right here.
Yeah.
This is an erosional surface, so it kind of goes back to this graphic. Yes. So as sea level fell, it exposed the stratigraphy to erosion, which then caused, like, there may have been other units in there, but it just ended on sandstone, and we kind of see evidence of that in a bit of weathering and brown, it's kind of like brown weathering almost on top of that sandstone that was in that unconformity. So, does this answer your question? Like, it basically, because it was eroded down, it then creates the next depositional sequence on top in an order that usually wouldn't have happened.
Okay, thank you.
Yeah.
Let's thank Annie again.
All right, so our next speaker is Becca Salati. She is going to talk to us about syn-depositional and post-depositional impressionism in the late Ordovician from the Wells Outlier.
All right. Hi, everyone. Thank you all for coming. As Annie said, I will be talking about syn-depositional and post-depositional tectonism which are just really big fancy words for faulting events that occurred during and after deposition in the late Ordovician from the Wells Outlier in New York. So you've seen this map before from Tamar and Annie, and so our study area is right up around here in the Adirondacks. And so the blue part represents the shallow carbonate basin, the green part represents the deepening foreland basin, and as Annie said, this gray part is the tectonic orogenic belt that is pushing up against the carbonate platform, allowing for this deepening to occur here in the basin. So again, this is the same figure that we saw with Annie. This is a good figure to give an overview of the faulting that is happening and occurring here as this orogenic belt pushes up against the carbonate platform and allows for this deepening with a lot of high angle normal faults and also some thrust faults in here. So the Wells Outlier is located in the southern Adirondack State Park, as you can see right here. And the Wells Outlier is a graben or basin that has been downdropped by high angle normal faults. And so it actually contains one of the most complete Cambrian and Ordovician stratigraphies in the entire Adirondack State Park. So as we were going to look at our study site, which is the Graymont Corporation quarry, we were allowed to take samples from basically all over the quarry, including their measured section right here, which they had blasted out, so it was pretty much available. And then the cores, we had 3 of them that were all drilled in 2006. And we also saw that the Black River group was exposed in the bottom part of the quarry, and the Trenton group was exposed in the northern part of the quarry. And up in the Trenton, we also found some other superficial features that helped us identify the presence of previous faulting events. So as Annie talked about, we had 2 main studies who had studied the Wells Outlier in the past. One was Miller in 1916 and one was Fisher in 1957. And from their descriptions and their what they noticed from the outcrops, we were able to come up with a schematic stratigraphic column. And so we would expect that the Proterozoic basement rock would be on the bottom, followed by the Cambrian, Potsdam, and Galway formations, and then the Black River group, and then the Trenton group, which then we would see the deepening from the limestones to a deeper environment that allowed for the formation of shales in the Utica Formation. And on top, we also would expect to see some glacial till and outwash. So this image here is from Miller, so it's old, it's from 1916. And what it shows is this is the Wells Outlier, outlined here in the red and the pink, and around it are the Proterozoic basement rocks from the rest of the Adirondacks. So my thesis was divided into 2 sections. My first section talked about the faulting events that occurred during deposition. And so we found a lot of evidence of this throughout the surface of the quarry, as well as within some of the cores that we were looking at. And so one thing that we found were these gneiss and quartzite cobbles that were within the Trenton limestone exposed at the quarry. And these cobbles were fairly well rounded, some of them a little bit flattened, but for the most part, they were pretty undeformed. There wasn't anything that was really displaced about them or around the Trenton. It all was pretty well formed here. And so we think that these were deposited at the same time as the Trenton limestone deposition. And so we also found this breccia block that was located in the quarry on the surface, but we're not entirely sure where it came from because it had been moved by quarry workers. But we do believe that it came from somewhere along an active fault zone, since it contains Black River group and also Trenton group stratigraphies, as well as a sandy matrix within it. So we think that it was along some sort of active fault zone that allowed for these units to come together, and also some sort of influx of sand at the same time, allowing for it to sort of shift around and become this new rock. So along with the sandy matrix that we found a lot of other units of sandstone, or other even just units that contained a lot of sand. And so this is a sandstone that we found on the surface of the quarry with a nice coral fossil in it. But we also found a lot of other sandy units and sandstone units within the cores themselves. And upon closer look at these sandstones, this is under cross polars in a thin section, we found that many of the quartz grains from the sandstone were actually fairly angular. Some of them were kind of well-rounded, but for the most part, a lot of them had at least one angular surface, meaning that they probably hadn't traveled very far before they were deposited into the basin. We also found other interesting minerals, such as this isotropic garnet here, that would be basement rock derived in origin, and so it was surrounded by this coarse angular sandstone, and so we believe that it probably came from somewhere up higher in the mountains with the Proterozoic basement exposed. So, in conclusion for this part, the gneiss and quartzite in the Trenton, the breccia block, the angular quartz sand, and the garnet, and other basement-derived minerals, we all believe to be evidence of faulting occurring at the same time of deposition in this basin. We think that perhaps some of these might have been from faulting up higher, where I guess the debris from the basement rocks or the extra rocks, like the basement-derived minerals and the quartz sand, would have come from up here and then deposited into this basin where they would just sit and not move so far. And also there could have been some faulting occurring in the basin, which would have allowed for the formation of the breccia block. So as I move into the next part of my thesis, I just want to remind you all about the expected stratigraphy that we would think we would see at Wells based on the interpretations from Miller and Fisher. So we would expect to see the Utica Formation up here, and then underneath would be the Trenton, the Black River, and then the Galway. However, when we looked at the core B3 was the strange one, and we found something very interesting. This appears the Galway, and then underneath it is this very fossiliferous dark mudstone. And upon first glance, it kind of looks a lot like the Utica Formation shale. So we took some samples and we made thin sections and epoxy mounts out of them, and we were able to determine in thin section that there were lots of fossils such as brachiopods and trilobite pieces and graptolites, which are all fossils that you would expect from the Utica Formation shale. And so we looked at them under the scanning electron microscope. And so our SEM images revealed that there was an abundance of pyrite grains that were angular and rounded and also in the rhomboid form that you can see down here. And then we also looked and found that there were other grains such as apatite and even this chert replaced fossil that resembled the fossils that we would see in thin section or in other Utica shale samples. And so we compared these to Mike Carbone's 2012 Indian Castle member samples. And so his samples are definitely Utica shale, and so we compared the mineralogy, and they were also very, very rich in pyrite and angular and rounded and rhomboidal form. And so since all of the mineralogy was the same and all of the fossils were pretty much what we would expect, and it even looked just like Utica shale, we interpreted that our unit was a unit of Utica shale. Although this causes a bit of a problem, because as you can see, I said it was below the Galway, and so as we were making our stratigraphic column, we had to place the Utica underneath the Galway, whereas I just reminded you that the Galway should be beneath the Black River group, the Trenton group, and the Utica. So as we were trying to figure this out, we eventually came to a conclusion that there is a fault present that has downdropped the Utica Formation underneath the Galway Formation and has allowed for the older rocks to go on top of the younger rock. We're not entirely sure of the dip of this fault, but we believe that it might be some sort of high angle fault because it does not show up in any of our other cores. It only shows up in core B3. And so we believe that it probably was a little bit more high angle. But it would be interesting to do future studies where we would take some drill cores from on either side of borehole B3, in order to determine the actual mechanics of the fault and the structure and see exactly what's going on there, since we haven't seen this fault before. So overall, we did find that there was evidence of syn depositional tectonism and faulting that occurred during deposition, as well as faulting that occurred after deposition, as we hadn't suspected this originally, but as we thought there might have been based on the amount of faulting that has occurred at Wells in the past. Thank you very much. Oleg.
As far as future studies that you were talking about,
Yes.
have you considered seismic exploration? It seems like the logical.
Yeah, so that's one that we kind of like had hoped that we could do a little bit more of, but we didn't exactly have the time or the resources. But that's definitely something that would give a better understanding of how the fault is moving and what's going on there, because we didn't know there was a fault here before, but based on what we found, that's what we assumed. So that would be definitely something to look into and to do. Yes, Ryan.
Could you clarify, so there are 3 boreholes in the quarry, and
Yes.
the fault is shown in one of the boreholes, but not the other 2 boreholes?
Yes.
Okay.
So
that's why you hypothesized that it was high angle?
Right, so that's what we thought, because they're all pretty close together. The quarry is kind of small, we could walk around it in just like an hour or and see everything. So we thought that since it only appeared in B3 towards the bottom, we assumed that it probably wouldn't, like since it didn't occur in these ones, it was probably some sort of high angle fault, which it could have been, or it could have been oriented a different way, but we're not entirely sure on the exact measurements of the dip. Thanks. Yes.
With the cobbles in the Trenton limestones
Yes.
that were of igneous rocks, metamorphic rocks.
Yeah.
Did you find any of Louville limestone that were less strongly rounded so that you really could consolidate the ideas on syn-depositional rather than pre-depositional fault?
Right. We did not. We mainly just found the cobbles that were from the gneiss and from the quartzite. There were some areas where like the breccia, they were kind of combined into one unit, but in that part we only found the gneiss and the quartzite.
And then any photogrammetry on the sandstone itself? To me, it looked like a lot of those grains are really sub-rounded rather than truly angular.
Right, so that one is actually from the surface, and so this one's just kind of like an example of the sandstone that was on the surface, and then these ones actually came from the core. So these ones were a little bit different, but there was just a lot of sand, and so some of them were sub-rounded, some of them were more angular. It just kind of depended on the exact samples that we were looking at.
Let's thank Becky again.
All right, so this next person, I was going to do an embarrassing picture, but Kevin already covered that on Tuesday. So instead, I'm just going to introduce Maggie McGuire, who's talking about the geochemical evolution of Espanola Island in the Galapagos.
All right. Nope, that's not mine.
Try it.
Yeah.
Where's that at?
Yeah. I'm gonna switch. Oh, yeah. How do I switch it? This one? Great. Take my badge. Good.
All right. Hi, I'm Maggie McGuire, and I'll be talking about the geochemistry of Espanola Island. These are the Galapagos Islands. They're located 1,000 kilometers to the west of Ecuador. And they're produced by a mantle plume, sorry, I'm a little shaky, located underneath Fernandina Island. And so these islands are located on the Nazca Plate, which is moving due east at about 51 kilometers per million years. And what this means is that the youngest volcanoes are in the west. Fernandina Island is the youngest at about 60,000 years old, and the oldest volcanoes are in the east. And so the oldest volcano, my volcano, is Espanola Island right there at about 3.31 million years old. And one of the cool things about the Galapagos is that there's extended volcanism. So as these volcanoes and islands are pulled away from the plume by plate motion, they still experience volcanic activity long after they leave the plume. And so, as you can see here, the eastern islands look very different from the western islands, and they have a completely different morphology. Eastern islands are much smaller than the western islands, and obviously don't display those calderas that you can see in this map. And so coupling these two observations together kind of led to one of the big research questions that I was going to investigate, and I'll talk about right now. And this is what's happening to the Galapagos as they age. How are these islands evolving? And specifically, what's happening as they're pulled away from this mantle plume source. So we went to Espanola Island, the oldest island of the Galapagos, to do the first ever comprehensive study of Espanola Island. And fieldwork looks like this, and that. And the only person who really enjoys it is Kevin. And so while we were there, we're trying to understand the evolution of the Galapagos over time by studying this oldest island. And so this is a picture of Espanola. As you can see, it's pretty flat. There's no evidence of a caldera. Its morphology is completely different than these western volcanoes, these young volcanoes like Fernandina. Okay, this is really exciting slide. So here we are looking at magma chamber behavior. As you can see, here we get Fernandina over here is red, and Espanola is this triangle, I think. And so old, like we said, looks different than young. And the important thing to get from this slide is that Espanola looks a lot different than Fernandina and is experiencing minor clinopyroxene crystallization. And so what is that? Why is that important? This. Minor CPX crystallization indicates that there's deep magma chambers at Espanola. And this is important because deep magma chambers, as we can see here, are different than Fernandina, which doesn't display CPX. So these young volcanoes have different magma chamber behavior than these older ones. Just again. So, what does deep magma chambers mean? Kind of why is that important for understanding the magma supply system? Looking here, MG number is a measure of magma chamber temperature. And as you can see here, Fernandina is more homogeneous along this MG number diagram, and Espanola is more heterogeneous. So Espanola has a wider range, of temperatures in its magma chamber. And we attribute that these patterns to a low supply of magma. So if you have interrupted flows of magma or just kind of these waning supplies, you're going to get different temperatures being held, which is very different from this young volcano Fernandina, again here in the western part of the Galapagos. And so Espanola's pattern looks really similar to these other volcanoes like Sierra Azul and Santa Cruz Shield Series, which is the oldest lavas on that island. And these volcanoes, this pattern has been attributed to their location, which is peripheral to the plume. So they don't often have this robust supply of magma that you see at Fernandina Island. Okay, so we kind of hit upon this first big question, interpreting the difference between east and west in their different magma supply environments. And the second big question that I looked at is the geochemistry between the east and the western islands. The geochemistry in the Galapagos is highly variable. It's really, really messed up. So what's happening, what I wanted to look at is kind of what's happening to the magma supply source, especially at Espanola, this oldest island. What does it look like? Our favorite map again. So in the Galapagos, like I said, geochemistry is highly variable. And what this means is that you get lavas that look like young Fernandina. They look like plume material. But there looks like there's also input from two other mantle reservoir sources. One of those is highly exhibited at Floriana Island, and it looks like ancient recycled ocean crust. And what this means is that it looks like there's kind of this material that has contaminated the plume at Floriana, and that's erupted especially there. And then one other thing at the Galapagos is like the third mantle reservoir source looks like upper mantle. And as you go from west to east, you get increasing contamination from this upper mantle. And upper mantle. And that's most highly seen at Genovesa Island up here, but again, you see it at all of these islands going west to east. All right, magma source. The colors on this map correspond to the colors on this trace element ratio graph. And as we can see here, Fernandina is red, Genovesa or upper mantle is orange, and Floriana, or that recycled ancient crust material, is blue. And so we're using trace elements here because distinct mantle reservoir sources have distinct trace element ratios. And these element ratios aren't affected by melting or by crystallization. They only change by mixing. And so when we're looking here, we're wondering where Espanola plots within these trace element ratios. Where does it exist in the geochemistry of the Galapagos Islands? And so when we plot Espanola on this graph, we see that it's generally in the middle of all three of these. A mixing of all three of these would have to cause this kind of cluster right here in the middle. As you can see, it does hit on all of these other end members, mantle reservoir sources, but it's generally right here in the middle. And so how do we kind of get to this middle composition at Espanola Island? So this is my proposed evolution mechanism for achieving those trace element ratios at Espanola. So as you move across from left to right, you're going to see that age is decreasing. Sierra Azul is currently erupting, and Espanola was formed about 4 million years ago. So starting with the consistent plume material, at all the islands of the Galapagos, there is a consistent plume influence. And so what is unique at Espanola is we think we see the beginning of this recycled ancient crust material, or this Floriana material. And so this material has a distinct beginning and a distinct end. And so we see this distinct beginning at Espanola. And so you see it reaches its peak here at Floriana, erupted here, and the tail end of this material is being erupted now at Sierra Azul. So another way that we have mixing to get the geochemistry we saw on the other slide is this input of upper mantle from what we believe is the Galapagos spreading center. So about 4 million years ago, the Espanola was much closer to the Galapagos spreading center, which is a mid-ocean ridge system. It is a component, it has a lot of upper mantle material. So while Espanola was forming, we believe there's more contamination from this upper mantle material because of its proximity to the Galapagos spreading center. And as you can see, the Galapagos spreading center actually migrates north away from the Galapagos, and plate motion takes the islands away from it. So we see decreasing input from this upper mantle material at Espanola. And so kind of how does this all come together? We propose that at Espanola, that it has had this waning supply of magma combined with this input from these three different geochemical sources. And that's why we see this really unique pattern at Espanola that we haven't really seen elsewhere in the Galapagos. And finally, like I showed earlier, fieldwork looks pretty terrible at Espanola, but it's really not, sometimes. And I would like to point out, fact check, Kevin Varga, waved albatross only live on Espanola Island, they don't live on Fernandina at all. And that's it. And then just thank you to everyone that's helped me along the way. This isn't Dennis. This is our boat captain. But I would like to thank Kevin, who is Mobile, Dennis, and Karen for especially helping me through this, and Deanna and Dave for helping me through the XRF process and making it, and everyone who's been super patient with me during this month, and this semester and this year. So, thank you. Julia.
Do you and your compatriots have any idea of a mechanism which would recycle that upper mantle, the crust area?
Yes, so that upper mantle recycled material is really weird at Floriana. But below the Pacific Ocean, if you've ever heard of the low velocity zone, the LOSVP, is kind of this slab graveyard underneath the Pacific, and the Galapagos lie right above it. It's very reasonable that a plume that's originating from this core mantle boundary could pick up something in that low velocity zone, and that could be that ancient recycled crust that we see.
Thank you.
Can I follow up on that?
Yeah.
Yeah, so for that to work then, so spatially, that stuff exists only beneath Espanola, but not underneath Floriana. And so are those spatial, like, because it's so deep down, right, that's like 600 kilometers or 660, right? So are you thinking that there's a boundary at 660 where on this side there is that ocean crust preserve and on the other side it's not, and then the plumes are just kind of coming up and not and sort of preserving that?
I think that, if I'm understanding your question correctly, I think that in the plume, like this ocean crust has been incorporated into the plume and it's localized to one specific area, specifically in this case, where Espanola and Floriana formed in the southwest. But I don't know if that's answering your question, but okay.
A follow-up on that one too. So there are a lot of plumes that are thought to come from this slab graveyard beneath the Pacific Ocean, and then also its corollary on the other side of the world, beneath Africa. Do you know of any other locations that are above these super plumes that also see this recycled oceanic crust? Or is this unique?
So there has been work done in Hawaii where it's not on this extent over millions of years, but over just a couple of years, because they sample there every day, you see this elevated change in chemistry. And so that is an example of of material being entrained in the plume, although I don't know if that's coming from this kind of slab graveyard. But I would have to look further into that.
Let's thank Maggie again.
And I'll introduce our next speaker. Our next speaker is Ackland Rando. He's going to be talking about the geochemistry of the Adirondacks alignment study. Excited. I don't know what happened.
So as Maggie mentioned, I'm doing the geochemistry of the Adirondacks, specifically following up on a limestone study that was done 10 years ago. So over the past 100 years, the Adirondacks have been heavily affected by acid rain. Acid rain occurs when sulfur dioxide and nitric oxide emissions are released into the atmosphere. This typically occurred in the Midwest from power plants burning coal, but also occurs from petroleum burning in cars and such things. So when sulfur dioxide and nitric oxide gets released into the atmosphere, it mixes with the water molecules and forms sulfuric and nitric acid, which is then deposited with deposition. As the winds moved from the west to the east, the Adirondacks were the first mountain range that they encountered, forcing precipitation, and acid rain affected the fragile ecosystems there. So acid rain's been linked to acidification of streams and lakes, which leads to fish kill-offs and forest decline. It's also been linked to soil acidification, which decreases the soil pH, causing nutrients to become immobile, as well as leaching calcium from the system. When calcium is leached from the system, snails decline because they use the calcium in their shell structure, and bird populations decline as they use the calcium in their egg shell structure. In addition, it affects vegetation as it depletes, as it's a vital nutrient for plant structures. In 1990, the Clean Air Act was passed, and emissions have been decreased. However, the effects of acid rain are still lingering and are predicted to take at least 50 years, if not longer, to fully come back to how they were before acid rain occurred. So with all that in mind, in 2005, a team of Colgate biologists, geologists, and their Colgate students applied 1.75 tons of limestone powder to 4 lime sites in the town of Webb, New York, which is just outside of Old Forge on the western side of the Adirondacks. So at each location, there were 2 plots formed. They were each 75-foot radius, where one was lined with 1.75 tons of limestone, which is a calculated amount of calcium lost in the past 100 years. And the other site was left unlimed as a control site. My study will focus on WE5, which is soil built on top of a glacial till, and WE10, which was soil formed on top of a glacial outwash. So this is just a picture of their liming application. As you can see, there was a lot of limestone being applied to the field. This is a picture in 2005 of hobblebush, which is vegetation used in my study later on. And this is a picture of a New York fern, also used in my study later on. While there's a ton of limestone on there, it's important to note that when precipitation occurred, the limestone would be washed off the vegetation and onto the soil profile to all be on the surface of the soil. That being said, however, when we went back last summer, these are packets of limestone just underneath the organic leaf litter, so not all of the limestone has been absorbed into the system, even 10 years later. So my study asked, after the liming, has the acidity of the soil changed? Has the soil chemistry changed, and can we actually see how deep the calcium has reached? And has plant chemistry changed? Have they used the nutrients that are being provided to them? So to do this, last summer, Di, Rich, Andy Sia, and Jake Marr and I went to the Adirondacks, and we dug a total of 6 pits, 2 on each lime site, and 1 on each unlimed site, to a depth of 40 centimeters, and soil samples were collected every 5 centimeters for consistency amongst pits. This was then air-dried and sieved for the less than 2 millimeter fraction, which was then used in soil analysis throughout the project. So for methodology, to measure how the acidity of the soil changed, we took soil pH and we measured exchangeable acidity through titration. For the soil chemistry change and how deep the calcium was reached, we used atomic absorption, which basically gave us a number of exchangeable base cations in the soil profile. And for plant chemistry, we used powderized leaves for total reflection X-ray fluorescence. So the first result we got was soil pH. As you can see, in the unlimed site, soil pH is very acidic at a level of 3.5 at 5 centimeters of depth, and 6.2 in the limed site. So remembering that pH is a logarithmic scale, it's easy to say that the limed averages are almost 1,000 times less acidic than the unlimed. That allows plant nutrient mobility in the lime sites for easier extraction by vegetation. It's also important to note that the paths don't cross until about 30 centimeters of depth, which is where we assume that the limestone influence is stopped. Next, we measured exchangeable acidity. Exchangeable acidity is just the measurement of how acidic each clay particle is in the soil. So if you use this top soil particle, the calcium, magnesium, and potassium are all good things. Plants can use those. But when acid is introduced, aluminum and hydrogen knock the positive base cations off the exchange site, and it becomes acidic. And plants can't utilize this. There's nothing here for plants to use. So using the chart on the left, exchangeable acidity is 4.6 in the unlimed averages, which is pretty high. And for the same depth, for 10 centimeters, it remains 0 in the lime site. That means that all exchange sites are being occupied by base cations for plant use. So what base cations are present? Exchangeable calcium is a high one. If you remember from one of the first slides, the limestone is 98% calcium carbonate, so that's expected. It's actually 10-fold higher in the first 10 centimeters of depth in the lime site than the unlimed site, and it impacts about to 35 centimeters. That's where we see the paths that across. And exchangeable magnesium is a little bit lower. You can see the units here are different, but it's still making an impact until about 15 centimeters, which is pretty good considering it's only 1% of the total makeup of the limestone. Another important thing to note here is that both magnesium and calcium experience a sharp decrease at 10 to 15 centimeters, and we think that that may have something to do with plant rooting depth. So if you look at the next slide, the graphs on the right are the TXRF data from the plant chemistry, and in WE5 they both show almost a double the amount of calcium uptake in lime sites and in lime sites for New York ferns and hobble bushes. And in WE10 there's also a large increase of calcium in lime sites compared to unlimed sites. So with that, we suggest that this missing piece is the amount of calcium being taken up by plants and utilized in their structures. So we can measure that, but we didn't measure that. So maybe the graph would be more linear decreased, and that the calcium may be affecting down to 45 centimeters in a positive way if it wasn't being utilized by plants and organisms within the system. So that was a pretty interesting thing that we're proposing there. And then One negative thing that we found, which we weren't quite sure about at first, was the large decrease in manganese. Manganese is used by plants for chlorophyll production as well as electron transport and photosynthesis. So it's really important for plant survival, basically. And it decreases a lot. So we weren't sure what to do with this, so we turned to the literature and we found that manganese deficiency often occurs in calcareous soils because the pH becomes too high, causing the manganese to precipitate out and become immobile, and then plants can't utilize it in their structures. So despite the decrease in manganese in plants, we did find several positive things. There was an increase of soil pH allowing for more mobility of nutrients. There was a decrease in exchangeable acidity, which in turn increased exchangeable calcium and magnesium on the exchange site structures of the soil. And plants are actually utilizing the calcium that was put into the system, which is a positive thing. We also calculated the depth at 30 centimeters. That was about the average depth that calcium and limestone seem to even out on the limed and unlimed sites. And we calculated the rate of transport to be about 3 centimeters per year. So overall, we found a lot of positive things. However, the Adirondacks are way too big and it's not feasible to lime the whole Adirondack region. So this is merely just a prediction of what may happen as soils continue to become less acidic. So I just want to thank Rich and DI for all your help in the lab and on this paper and on this project, as well as Jake Marr and Andy Sia. They dug in the dirt with me when they didn't have to. And any questions? Yes.
Did you say that there's a prediction on how long it would take to get back to normal calcium?
Yeah, so it's actually pretty widely debated. Some authors are saying the general consensus is at least 3 to 4 to 5 decades, but some authors are predicting it to be 100 just because that's the period of time that they were affected by acid rain. But it's really not, there's not a set number that's known for that.
With the effect on magnesium, or manganese.
Manganese.
Yeah. I mean, that was only because of liming, or was that a natural process from acidic kind of?
Do you mean the decrease?
Yeah.
I would say that it was based on liming, because in the unlimed sites it still remained pretty high. What I do question though is it higher in the unlimed sites because it's acidic? I'm not sure about that. Yeah.
So obviously, like SOx content in the air, right, has been going down a lot in the region, and probably like has over the last 10 years as well. Did you factor that in at all, how air quality could be affecting the results of your study?
I didn't actually, because we had the control site, so they would also be experiencing the same air quality.
Okay.
10 years later, if you were approaching the sites, could you visually say that was probably limed versus unlimed in terms of vegetation density or health?
It's actually funny, when we were out there, the lime sites had trout lilies present, and the unlimed sites did not. So there was a definite change in vegetation between the two sites, but it would take a keen eye.
All right, let's thank Ashley.
So next up is Ryan Clements. He will be talking about kinematics and temperature conditions of myelinization and a metamorphic core complex in Arizona.
Thank you for that introduction, Ashley. I'm Ryan Clemens. I'm excited to speak with all of you today about my research on kinematics and temperature conditions of myelinization in the Harkavar metamorphic core complex. I know it's a mouthful. So the Harkavars are located in the Basin and Range province, which is shown in gray, which extends from British Columbia, Canada, down to Sonora, Mexico. The province is understood to be a product of crustal extension dating back to the early Miocene, approximately 20 million years ago. Sorry, just 1 second. Sorry about that. My name is Ryan Clemens. I'm excited to speak today about my research. The Harkavars are located in the Basin and Range province, extends from British Columbia, Canada to Sonora, Mexico. Dating back to about 20 million years ago is when the core complex is thought to originate. The Harkavars are one of many core complexes that are identified throughout the province, shown here by the black splotches, and the mountain range itself is located in west central Arizona. So the formation processes behind core complexes are somewhat of a controversial issue in the scientific community. Kate Hardock touched on this a little bit in her talk, and that is kind of what my research, her research, and Martin's research is trying to grapple with. And I want to touch on kind of the basics of a core complex for a couple reasons. The first is for those in the room not familiar with core complexes and how they are thought to work. And the second is that it provides pretty important backstory for the research that I present. So here is a model of how a core complex is thought to originate, and there are 4 main characteristics of a core complex. The first is that they accommodate extensive displacement, oftentimes greater than 50 kilometers in the lateral direction. The second is that that displacement occurs at a uniquely fast rate, as much as 3 centimeters a year. The third is that they are thought to develop at low angles, generally considered to be about 30 degrees. And the fourth and most pertinent to my research is that they occur at that brittle ductile transition, which is in the crust about 10 to 15 kilometers below the surface. And in the case of the Harkavars, you have a brittle upper plate ductily shearing a lower plate and effectively creating a myelinitic shear zone. So the Harkavars are part of a series of ranges in the Basin and Range province. They're flanked by the Buckskins to the north and the Hartwell Hollows to the south. They are generally understood to be part of a larger normal fault system known as the Bullard Detachment Fault. The direction of extension along this fault is southwest to northeast. And as you can see, almost the entire Harkavar range is a part of the lower plate footwall, that myelinitic shear zone. So the question that I set out to answer is, does temperature increase in the direction of the fault? And the reason this is a good question to answer is because a thermal gradient would represent a depth profile of detachment fault crust. So this might suggest or provide evidence for the initial angle of the fault, which is, as of now, kind of up in the air for debate. So what techniques might we use to see if there is a thermal gradient? Well, thankfully we have these 2 really cool things called dynamic recrystallization and lattice preferred orientations. Dynamic recrystallization is changes in the shape and size of grains during metamorphism, and the 2 minerals that we are concerned with for the purposes of my research are quartz and feldspar. They're the most abundant minerals in the Harkavar myelinites. Feldspar, on the right here, as you can see, has a tendency to behave brittly during shearing. Quartz, on the other hand, on the left, behaves ductily under a wide range of temperatures, making it an excellent indicator for dynamic recrystallization and constraining temperatures. Previous research studies have offered a proxy for determining deformation temperatures in quartz samples, and there are 3 stages of dynamic recrystallization in quartz. The first is bulging recrystallization, which is characterized by small recrystallized grains along grain boundaries. That's a low temperature texture. The second is subgrain rotation, which is characterized by flattened grains with distinct subgrains, a medium temperature texture. And grade boundary migration is the third texture at this point, with intergranular deformation features having largely been erased. And so by examining these 3 quartz textures in thin section, we can get a better idea of the temperature conditions that the quartz recrystallize at. And so moving on to lattice preferred orientations, LPOs of individual quartz grains can reveal dominating slip systems within samples. So the top figure is a stereonet plot with C-axis clusters and the type of slip associated with each, either basal slip, rhombohedral slip, or prism slip. And the bottom figure is a temperature gradient that is correlated with each type of slip. So basal slip is considered to occur in quartz up to about 400 degrees. Rhombohedral slip can occur in quartz up to about 600 degrees. And above 600 degrees, prism slip is the lone slip system that is active. So the methods that I used specific to my research to study the thermal gradient and kinematic indicators were petrographic observations, as well as EBSD work, electron backscatter diffraction, to study LPOs in the sense of shear. Quick plug about EBSD to explain a little bit how it works. It's used in the SEM, and the electron beam is focused on thin sections. Electrons will hit the grain and then diffract to form interference bands, which correspond to underlying crystallographic orientations. And then you can plot the LPOs to reveal the dominant slip system within samples. So I analyzed 10 samples across a 20-kilometer transect of the Harkabar Range. And in discussing my results, I will move from north to south, effectively moving away from the detachment fault. And so the northern samples generally showed high temperature. Here we see grain boundary migration as evident in the northernmost sample. We know this by the serrated and amoeba-shaped grains. And again, this texture is high temperature deformation. Here's another sample derived from the northern section of the transect. We see the polygonalized grains with well-defined boundaries suggest that the sample sat at high temperatures for an extended period of time, effectively allowing the grains to anneal. Moving south from the fault, we see lower temperature textures. Here we see subgrain rotation as well as bulging recrystallization. And continuing along the transect, we see further bulging recrystallization in addition to brittle quartz textures. And so this sample here exhibits microfaults as well as crystal growth within fractured veins. And this suggests that the sample underwent brittle deformation after the dynamic recrystallization window closed and after peak temperatures were reached. So to quickly summarize the petrographic results, we see a loose thermal gradient going from north to south along the transect. And so now let's see if EBSD results show a similar trend. And as a whole, EBSD results offer a somewhat similar but clouded picture. The northernmost sample analyzed under EBSD shows clear top northeast shear, and it shows a wide array of temperature conditions. It shows basal, rhombohedral, and prism slip. It is dominated, however, by rhomb and prism slip, as evidenced by the cluster of LPOs in the center. Continuing south along the transect, lower temperatures become apparent. Here we see clear basal slip and top to the northeast shear again. And so as a whole, between petrographics and EBSD data, we see a thermal gradient throughout the transect. However, the southernmost sample does not reflect this trend, and I will talk about that sample now. Sample 115 exhibits clear grain boundary migration, as well as rhombohedral and prism slip. And the combination of this data suggests that sample 115 underwent high temperature deformation, likely greater than 500 degrees. And so it's a little bit, I guess, difficult to kind of piece that into the puzzle, but I will do that in a moment. So as a whole, to answer the question that I posed, is there a thermal gradient? Yes, there is, and the data broadly support this. This can tell us a little bit about how and what angle the fault initially initiated at. Now, what about sample 115? There are a couple different ways we can read into this. And so one explanation is that the fault could be a result of a plutonic intrusion. So if there's a there's a pluton and outcrop in the Buckskin range, which is one range to the north. and so this idea is not too far-fetched. A pluton could potentially superheat the country rock and cause contact metamorphism of the sample. That being said, there's no pluton in outcrop in the Harkavars, so a more plausible explanation for sample 115 is that it exhibits relic textures, which are commonly evidenced via overprinting. And so overprinting we're seeing throughout all of my samples, and this one, here's an example of how we can have brittle textures overprinting ductile textures. On the left, you'll see quartz ribbon grains and quartz bands behaving ductily, and then on the right, you'll see quartz ribbon grains and quartz bands with microfractures within those. So here we have brittle fabrics overprinting ductile fabrics. And so piecing this back to sample 115 and the Harkavars in general, it is possible that the 20-million-year-old Miocene myelinization event is predated by some other metamorphic event. The core complex could have later developed in the geologic history, and the textures that we see in the Harkavar myelinites could be overprinted textures. So if sample 115 were shallow enough, there is reason to believe that it was, newer textures would not have developed on that sample. So to, I guess, going forward, if future studies were to build off of this work, I would recommend completing a longer transect that extends all the way to the fault with a higher resolution of samples greater than 10. And as a whole, core complexes remain somewhat of a geologic mystery still, and my work as well as Kate Hardock's work is trying to piece that together and contribute to the growing body of research about metamorphic core complexes. So thank you all. Particularly, there are two people I would like to thank. The first being Kate Hardock, my partner in crime in Martin's lab. She's been absolutely awesome. She's not here today, but thank you very much, Kate, for always keeping things light. And then also, I would really like to thank Martin Wong. Martin, thank you so much for your candid advice and your continued support throughout the past year and for generally just putting up with me. So thank you very much, and I would like to field any questions.
So, both of your methodologies showed a temperature gradient with the exception of one site. But if I understood one of your slides correctly, that temperature gradient was slightly different in the two methodologies. There was an offset temperature case, and if so, why?
So, yes and no. I will say two things. The first is that the one method had a higher resolution of samples with 10, and then we selected 3 samples based on location and based on the petrographic observations that would be good candidates for EBSD work. And so, in order to, I guess, fully answer your question, I think we would need a higher resolution of EBSD samples, but there were a limited amount of EBSD capable samples within the 10 samples that we selected. So I'm not going to say that yes, there is a difference in the thermal gradient, but there could be. I would need, I guess, more data. So if that answers your question.
Am I allowed to ask questions?
Yeah.
No.
I'll talk to you.
So yeah.
Okay, well, let's thank Ryan again.
So I would like to welcome Mike Dubois, aka Doobie, to the front of the room to talk about geochemical analysis of pyroxene megacrysts from a massive anorthosite in the Adirondacks region. Thank you.
I have to say I was really, really nervous about this, and then I got a text from my older sister about an hour ago. She's like, I think I'm going into labor. I'm on my way to the hospital, so this should be a breeze, relatively.
Congrats, Uncle.
Well, not yet. Well, plus I'm already an uncle, but yeah, thank you. All right, so geochemical analysis of pyroxene megacryst in the Grenville province in the Adirondacks. Where's the spot there? Nice. Okay. Is there a clicker up here? Baseball, cool, okay. So this is the Grenville province. It's the eastern margin of the Canadian Shield. The area that I'm looking at is this little southeast outlier known as the Adirondack Mountains. So I'm just going to zoom in on that. There we go. So this orange region represents the anorthosite of the Adirondacks. This striped region is the Mandurite, Charnockite, granitoid suite related to it, essentially thought to have been from crustal interaction with the anorthosite as it rose as it died here. So this is a map of the Grenville orogeny and affected rocks. As you can see, it is a global phenomenon, a global geologic phenomenon, and is also very complicated as evidenced by this next figure. So this is the Grenville orogeny as a whole. It's sort of a misnomer though, because there are several discrete orogenic events within the Grenville orogeny, and none of them are really agreed upon. It's widely thought that it started with B-type subduction of the oceanic plate, leading to accretion of arcs onto the continental plate, and then down here you'll see that there was a time period of crustal thickening that is thought to have been from continent-to-continent collision. But like I said, it's very complicated, and we don't even know what continent was colliding with the eastern margin. If you can imagine that, what continent? We don't know where it went. So if you have more questions, just ask Bruce. He wrote the paper on it. So this is the widely Amazonia, right? Okay. Well, this is the widely accepted but not universally accepted sort of model for where anorthosites come from. As you can see, a big magma chamber forms near the boundary of the crusted mantle. As crystallization occurs, the heavier mafic minerals sink down to the bottom. Lighter minerals rise to the top, namely plagioclase, which makes up the vast majority of the Adirondack rocks. And then through thermal and buoyant, because of thermal energy and buoyancy, these diapirs rise to the surface. It is analogous to, say, a hot spot rising through the crust. The final emplacement is estimated to be about 3 to 6 K-bars, so like 15 kilometers to 10 kilometers beneath the surface. One of the confusing things about anorthosite for a long time was this lack of mafic minerals. According to our model of what happens with melting in the lower crust, you would expect 50 to 70% plagioclase to be formed. We see 90 at the top. So this model was really the first one that solved that problem. Another question is, what happened to the mafic minerals? Here they think that they sunk down, but part of this is that we see some of those mafic minerals in the form of pyroxene megacrysts, which is mainly what I was studying. Pyroxene, specifically orthopyroxene, generally has magnesium and iron in the cation locations, but can substitute aluminum in. And through experimental studies, Emsley specifically found a calibration for the depth that pyroxenes formed and the amount of aluminum that they had. So essentially, more aluminum means formed at a deeper depth. So now I'm going to show you where I got my samples from. This is a map of all the samples collected. Yellow is the ones I collected with Kevin Varga in the Adirondacks. Red, William found in 1998, and then green is from a paper by Jaffe. Oh, and these numbers here are the weight percent of Al2O3 that were found in each sample. So I brought the samples back, took them to XRF. This picture was taken by a potato, sorry. And then we also studied them with the handheld XRF device, commonly referred to as the X-ray gun. There was a lot of doing that. So I'll get into the results of those tests later, but first I want to get into the texture scene. This is a common texture we saw. This is actually the very first pyroxene that we found. The thing about anorthosite is it's very hard. You can't knock these minerals out, so I wasn't able to get this one with me. But you can see garnets forming around the outside of the pyroxene and a subhedral or anhedral sort of crystal face. Here's another common texture, is subhedral blocky textures. You see here it is zoomed in. You see some crystal face, but not much. Other textures seen, this is another subhedral phase. I actually used a software that annotated the pictures, didn't save another copy of them, so there's little quirks like this, and like this arrow pointing to nothing. Another texture seen here, if you look very closely, I know it's difficult to see, but you see black shiny mineralization here around the outside of this giant pyroxene. That was common, we saw mostly mafic minerals that were recrystallized. I don't have much to say about this picture, but it's fascinating. This is the only time I saw this in the field. This is like a linear, sort of a dike-like shape of pyroxene megacrysts, which sort of, you can infer probably movement of material, maybe in a semi or fully liquid state. This is not my beer bottle, I don't litter. We also saw intergrowth with iron oxides and mafic minerals in general. And then one other common texture we saw was this intercumulus growth. You can't really see it too well because it's the nature of it's this hard thing to capture in a photograph. But if you see here, there's a pyroxene coming down here, and there's a little strip here, and then some large ones in here. Now, when I got this rock, it just looked like a lot of little pyroxenes, but it turns out when you slab it up, they're all connected on the inside. So essentially, intercumulus growth that was not clearly visible when I first looked at these rocks. This is another common texture. And then as far as the crystals themselves, in every sample I found, there's significant exsolution lamellae. Some like almost on the centimeter scale wide, which is like quite large. Mostly plage, more pyroxenes exolved out of the mineral. But so what is all of these textures sort of telling us? So we see a variety of textures, a variety of degree of intercumulus growth to solid crystal faces. So I think what I got from it is that it's sort of pointing to a wide variety of crystallization settings, which would, potentially go in with a theory of a lot of different depths at which these minerals are forming at. So right now I want to talk about the two main models for where these pyroxenes come from. The first is that the pyroxenes form at or near the moho and are pulled up by the diapir as it rises. The second is that these form at or near the moho, pulled up by the diapir, and then continue to form as the diapir rises through the crust. So I think texturally this supports the latter theory, because it seems that there's a variety of different sort of settings for these minerals to crystallize at. So this diagram is really just showing you the ALTO3 amounts that I got and the relationship to pressure. You'll see here, it doesn't take a keen eye to see that there are two outliers. I'm not going to get too much into it now, but if you would want to ask about why those outliers are outliers, what they mean, you can reserve that for the question portion of this presentation. But there's a reason, but I don't think that they're geologically significant, so I'm going to continue on that. This is what happened when I compared my data to the other studies of these anorthosites to see if it was consistent with what other people had seen. The peak here is similar. I think largely they are consistent. You see a second peak here with the inclusion of everyone else's results. So this is two studies and then my study all put together. And you see the second peak here, and that is because of the RAP, the Anorthosite province in Norway. When Bybee studied these, he found really, really high aluminum contents, much higher than anyone else found. And that sort of is the creation of that second peak in the previous histograms. So overall, my aluminum contents were consistent with what we've seen in other studies, and they also show a range of aluminum values, as you can see, from like 2 to 9, plus the two outliers. So in conclusion, what I get from these aluminum values, and also from the textural evidence, is that my data supports Charlier and others' theory that these pyroxenes formed in situ as the diapir rose through the crust. Then, had to finish with a pun. I have a lot of people to thank because if a thesis is a marathon, mine is a marathon that took 2 years. So I want to start first and foremost with William, who's watching on that screen. It wouldn't have been possible without him. Kevin Varga, who helped me collect my samples, and my gracious professors from this semester who were very forgiving of all the work I was putting into this. So with that all being said, I would like to open up for questions. I gave you guys 2 questions. I gave you 2.
Okay. What happened with the outlier?
Okay, so how do I go? Okay. So you'll see this sample that I showed you a picture of, this one right here, with this border. So this was actually one of the outlying samples. It was this NB8. It had an aluminum Al2O3 of like 13 or 14%, which was way higher than anyone had seen in any previous studies. And what I believe happened is when separating this crystal from the greater rock to just isolate the pyroxene, I believe that it was contaminated by some of this mafic mineral on the outside. They're all very dark, and when you get them in a small powder form, I believe that I may have made a mistake in picking out the pyroxene, simply put. The other mineral that was an outlier also had a border crystallization too.
Can I follow up on that?
Yeah.
So you showed all of those exclusion lamellae kinds of things. So do you feel confident that, like, I'm not sure even how you prepared your samples for like XRF, but do you feel confident that your pyroxene samples like avoided exclusion lamellae? Like, is that a problem that you're worried about?
I don't think that should lead to a problem with aluminum contents because exclusion lamellae is exolved from the mineral itself, from the crystal itself. So it should preserve the same sort of elemental ratios. I guess one thing that might occur is, you know, as you can see in the exclusion picture, right there, it's not all the same mineral. So perhaps the exclusion that I did put into the sample might have been, you know, a section where it was a lot of iron oxide instead of, you know, the general mix of iron oxides, plage, pyroxenes. And that could have affected it. But I feel pretty confident that if that did affect them, it did affect them to a very small degree. You'll see the error bars in my paper. Any other questions? Yeah.
So you imagine these diapirs like rising up through the crust and forming pyroxenes, so like as a sort of like melt bubbles sort of thing? How do you picture that?
It would be a mush, similar to what you described with your Galapagos magma chamber. So it would be at least a partial melt of this of the magma formed pooled at the base of the crust, and then the pyroxenes and plage that have already crystallized at the base of the crust. So it would be a mush. It would be a partial melt that is continuing the crystallized pyroxene at a decreasing content of aluminum as it rises. Any other questions? Bruce, I know you have 2.
All right, well, let's thank Mike and all of our speakers.